So, synergies between Swarm and MSS. Let's now look at some science opportunities. First, we'll look a little background, history about Swarm. Then, mainly we'll look at the opportunities that we get with so-called close encounters between MSS and the Swarm satellites. We'll also quickly look at the improved local time description that is possible if we combine Swarm and MSS data. And finally, some outlook for some suggestions for MSS2. So, yeah, next, good. 25 years ago, 1998, we submitted our first proposal to ESA about Swarm. That was actually 1 year before the launch of the Earth satellite, 25 years ago. At that time, we proposed 7 satellites. It consisted of 6 satellites in 2 orbital planes, or in polar orbits, augmented with a 7th satellite in a low inclination orbit. That was at that time thought as the French contribution to this part. So obviously that has not been implemented by ESA. So, yes, but now, 25 years later, with MSS-1, we finally get this possibility. Okay, let's now look at close encounters. This is the altitude range of Swarm Alpha, Charlie, Bravo, and also of MSS. And you see from the altitude range, there is some overlap. Let's then look at the orbits. And I think it's very important to remember or to realize that a lower inclination orbit is a little different from a polar orbit. We are used to polar orbits, which means that to take one orbit, then we have coverage of the northern and the southern hemisphere on the day side and on the night. The situation is completely different with a low inclination orbit. It essentially means that for 3 weeks, you only have day-side data in the northern hemisphere and the corresponding night-side data in the southern hemisphere. And then the situation has changed after 3 weeks. So it is not possible to make some kind of snapshot model if you just take a few days with a low inclination of satellite. That is possible with a polar orbiting satellite, but that is not the advantage of a low inclination orbit. The low inclination orbit is good in measuring, observing what is going on in local time variation, what is going on in longitude separation. Okay, if we now look at the local time of the ascending node, you see here in red, blue, a Swarm, and in yellow we have Makausa. That's the local time of the ascending node. If you then add the local time of the descending node, well, we basically double it. And it means that we have close encounters every 52 days. We have counter-rotating close encounters every 52 days. And we have co-rotating close encounters every 52 days between Makausa and each of the other satellites, M Alpha and Charlie. Okay, that means basically MSS has a close encounter with each of the satellites M from Swarm every 3 weeks. So let's now look at an orbit prediction for half a year. This is the inter-satellite distance between Alpha and Makausa. And you can see that they become really close. And let's now look at 3 of these events at the end of August, middle of September, and end of September. In particular, we will look at this one here. You can see that for 6 hours, we have 4 close encounters where the satellite comes as close as 40 kilometers or so. If we switch a little bit the time of Alpha, then we reach separations of less than 5 kilometers. So these are really close encounters. And let's now look at one of these examples that is on the 7th, and that is on the 11th of September. In the top panel, you'll see the measured magnetic field intensity on these 3 satellites, Macausat, Alpha, and Charlie, after removal of a model of the core and lithosphere. In the bottom, we see the inter-satellite distance. In particular, these are the distances between Macausat and Alpha and Charlie. So here we see the orbits. We have four close encounters, 1, 2, 3, 4, 2 on the day side and 2 on the night side. And if we now look at what is the magnetic field difference, actual measurement, Macausat minus Swarm Alpha or Charlie, as a function of the satellite separation here. Then you see that this is really exciting because it's less than 1.5 nanotesla. If this was a geophysical signal, then we would expect that the magnetic field difference should decrease if we come closer and closer. And eventually they should merge at 0. But that's not the case. So there is obviously a difference. And this is likely due to not optimized magnetic calibration on each of these satellites. So by looking at these close encounters, we have a unique opportunity to improve the calibration on all these satellites, and also, of course, new opportunities for science. If you look at 1 year worth of data, well, here I've made some orbit predictions. It turns out that the distribution of these close encounters is rather good in longitude and local time. And we have about 20 close encounters every year. Okay, now the improved local time description. Here you see axial orbits for Alpha, Bravo, and Macausat. I have not used actual data here, but one of the opportunities that I see is in ESD index. This is a large-scale magnetospheric field aligned with the dipole axis. We probably, by merging all these data, we can do much better. In particular, looking at the local time dependence of what's going on. In the external field is presently the main limitation of further improvement of core and cluster fields. If you can improve the space-time description of the external field, then in turn we will also be able to improve core and cluster field. It will also help to improve the determination of the 3D mantle conductivity, because for that we need a good description of the space-time structure of the external field. Okay, let's now look at the next satellite and some ideas for Macausat 2. Well, we started to do some simulations based on what lithosphere field studies can be done if we have a satellite in elliptical orbits. And here, this is the general principle, and then we have applied this to Macausat 2. But the basic idea is the following. Here, what you see here is the lithosphere field spectrum. So it's the power independence on spread of harmonic degree. That is what we see on ground. This is what we presently see in Swarm. So there is a huge difference between, for the high degree field, what we actually sense with Swarm and what we see or what we want to see. Now the situation is better if you look at CHAMP, which still CHAMP is the main source for lithosphere field modeling because it was at an altitude of 300 kilometers during the last months. Then we have this proposal to ESA and Daedalus. Anja has already mentioned it. Unfortunately, it was not yet selected. But then we have Macausat. And here you can see that Macausat 2 with an aperture of 200 kilometers really will make big change. So at spread harmonic degree 180 here, the lithospheric field is 240 times stronger at a Markowsat perigee compared to what we hopefully will get at the end of the swarm mission. And it's 100,000 times better what we presently can see with swarming. But what is important here is that we have a low perigee. What you see here is the distribution of how long time does the satellite spend at different altitudes. It turns out for these simulated Markowsat satellite, and here I've used 200 times 5,000 kilometers, which is not the latest value. Less than 5% of the time are spent at altitudes lower than 250 kilometers. But still, these data are so essential because they have a much larger lithospheric field signal. And we can see that, I switch this, well, we can estimate what is the expected variance of the Gauss coefficients, independence on spherical harmonic degree. And we have done that for a simulated orbit and compared that with a reference orbit in 350 kilometers. And it turns out that at spherical harmonic degree 180, we have 1,000 times smaller variances compared to this reference orbit, despite the fact that only 5% of each orbit is spent at these low altitudes. But what is essential is to have a perigee as low as possible. Here, I did some simulations. So what happens if we can, instead of have 200 kilometers, what happens if we go to 190 kilometers, 180 kilometers, so and each kilometer counts. Yeah, we can really improve on that. So since this is a discussion meeting, I would like to open for some discussions here. So how low is it possible to have perigee? What is the limiting factor in order to increase even or decrease even more? And what I also think is very important is when. As scientists, of course, we want to have the data now, as soon as possible. But it might be worthwhile to wait a little bit, because to fly a low perigee mission during solar maximum is not good. And we also have the disturbance field from the ionosphere. So it might be worthwhile to wait a little bit and to wait for the next solar minimum. Thanks for that. And finally, well, we are prepared and we are looking forward to work with the MSS team and work with the data. Thank you.